So while we saw in the last part that CO2 and temperatures are closely related to each other. If CO2 goes up, temperature goes up. If temperature goes up, CO2 goes up. If temperature goes down, CO2 goes down. And so there is a close link between these two. Okay? But which one triggers which? Okay? Did temperature anomalies lead or lag CO2 anomalies? Later on you will learn about the significance of CO2 as a greenhouse gas, but at this point we already have a little bit of look at this lag between these two properties. Okay. All right, let's have a look at some reconstructions. And this is taken from a work by Chacun et al., published in 2013. And they not only looked at ice cores, but also reconstruction of temperature and CO2 anomalies from other data, from microfossils and other types of data. Again, the distribution of the data sites is shown on this graph. You can see that there are sites in the northern hemisphere and there are sites in the southern hemisphere, including Greenland and Antarctic ice cores. Let's have a look at the reconstruction. Okay, it's shown on the next slide. Let's get this going here. Click. All right. Here's the reconstruction. Okay. It all actually started with the Earth orbital cycles that triggered a warming in the Arctic approximately 19,000 years ago at that time. So let's have a look at what's shown here, the reconstruction. There's a little bit busy, this graph. The x-axis is time, starting 22,000 years ago, ending up at the present, a little bit before the present, okay? And there are shown three curves here, okay? The CO2 concentrations are the yellow dots, and you can see that the yellow dots also have horizontal black lines. And these are actually error bars. It's the uncertainty of the timing. Okay, it's the uncertainty of the timing. You learned that you can date samples using radioactive isotopes, but it comes with an error, and the error is shown here in terms of, it can be a little bit older or a little bit younger. Okay. All right. Time series, you can see that the CO2 concentrations are relatively low, below 200. It's this axis that you have a look. This are the CO2 concentration, and you are at about maybe 186 or something like that. Okay? Parts per million in terms of volume, and then you can see an increase. You can see an increase in two different steps. Yeah, okay, and two different steps of that. Okay. What are the other curves? The blue curve is the average global temperature. Okay, blue curve, and you can see that the CO2 change comes first, and then it's followed by the global temperature. Okay. And you can see it again in the second. CO2 comes first, and then it's followed by the global temperature increase. And you can also see here in the global, the lag is about 500 years, 600, 700 years. The CO2 increase comes before the temperature increase globally. Okay? But it's different in the southern hemisphere. In the southern hemisphere, it looks confusingly different. In the southern hemisphere here, the temperature signal, it comes earlier. in the southern hemisphere. So temperature leads CO2 in the southern hemisphere. Okay. And again for the second phase of the event. So it's not as easy as you think. There are complex feedback mechanisms occurring. It's different northern hemisphere and southern hemisphere because there's something happening. Various climate feedback mechanisms that you will learn about, but I just want to introduce you to the bipolar seesaw. And this is a little bit shown here on the next slide. Okay. Shows you a reconstruction of temperatures, essentially, for Greenland and Antarctica from 30 to 50,000 years ago. And you can see changes. These are actually the data for the delta 18 oxygen isotope. Two different types. But anyway, let's just see what happens here. And that is really, really interesting. Let's first of all, without any interpretation, look at the signal. And you can see if you look at these gray bars that Greenland has a low, indicating a cold climate, while Antarctica has a warm climate. Okay, and you can see a second event here, warm Antarctica, cold in the Arctic or in the Greenland. This is the Greenland region here. And this is what we call a seesaw. You know, it's opposite. It's up and one and up. But however, it's actually not so. There's something happening here in these areas. I will not go into the details. I'll just show you that it's both events that you can see are actually start before these events. There's increase in temperatures, global increase in temperatures. Both Antarctica and Greenland have this increase. Then something happens in the northern hemisphere. You get the drop, which is a sharp drop in the northern hemisphere. You also get a drop in the southern hemisphere, but not so pronounced. So it stays relatively high up. Okay, but it gives you the impression, or it actually, you get the seesaw effect. Greenland, cold, Antarctic, warm, although it's similar processes happening in both hemispheres. You can see the second event called H5. It's actually links to Heinrich events. But anyway, you can see that in both before is a global warming here. Both increase, then something happens in the northern hemisphere, sharp cooling, less in the southern hemisphere. Okay? So if you look with a naive view at these temperature records, you can actually get confusing results in terms of one region lags the other one. In terms of, so there are these delicate climate feedback mechanisms, okay, which actually involve ocean circulation changes. Okay, so this is the bipolar seesaw, and just learning about that, you can actually expect surprises in the way the Arctic or the Antarctic responds to global warming. Not that much the Arctic, but the Antarctic. Anyway, okay, so this is the link to the bipolar seesaw. Okay, study questions. What are Milankovitch cycles and why do they influence climate? What is the characteristic timescale of ice ages? How were CO2 and air temperatures related to each other during ice age cycles? What is the bipolar seesaw? And which process has ended the last ice age? Thank you very much.